come on with me and let us start with the revision of alcohol, phenol, and ether. So get a pen and a paper and let us finish the quick revision of this chapter. No. This much is not enough. You need to read some more. This is the memory map which will revive you of your, whatever you have studied. Okay, so without wasting time, let us start with this memory map. You can use this memory map, and whenever you think you want to do a practice, you want to remind yourself. So this is how it goes. So first we will start with the methods of preparing alcohols, and next we'll go to chemical properties. So it's together. Okay, so do not see the right side now. Let us go to the left side and start. So when we have an alkyl halide, which we have discussed in the last revision also, when we have an alkyl halide and we are trying to prepare an alcohol from the alkyl halide, you can use aqueous KOH or aqueous NaOH, or even you can use silver oxide in moisture. So what it will give you, always the halogen will be replaced with the OH, which is coming from the nucleophilic partner, which is the OH of the KOH or OH of the NaOH, or silver hydroxide is forming, which transfers it and converts it to the alcohol. So here comes the first method. The second method is from an aldehyde. Aldehyde, you know that you have a double bond OH. It is simple, consider this double bond O as, a brother and a sister, as a carbon as a brother and oxygen as a sister. So you need to, they're hungry. The double bond means they're unsaturated, they're hungry. Let's speak it that way. So, you need to convert it to an alcohol. So you have to give the oxygen part a hydrogen and the carbon part also a hydrogen, and you get the alcohol. So this is simple. Supply any hydrogenating agent, hydrogen in the presence of platinum or palladium, or even lithium aluminum hydride, or even sodium borohydride, which will satisfy the unsaturated species and make it saturated, or the hungry kids are fed and they are happy. Okay, so you get an alcohol from an aldehyde. And the same thing works for the ketone also. Okay, same thing works for the ketone also. You take hydrogen in presence of platinum or palladium or even nickel, it works out, and lithium aluminum hydride, it will give you the respective alcohol. But the difference in the aldehyde and the ketone is that, the alcohol which you will get from a ketone will always be a secondary alcohol. All right, the alcohol from the ketone will always be a secondary alcohol. Going on to the next one. So you have your carboxylic acid, RC double bond OOH. Once again, what do you need to do? You have a unsaturated species, which you need to saturate it. So put as much as hydrogens as possible. I mean, we are not working out the mechanism. So saturate the carbonyl carbon with a lot of hydrogens, and you get your alcohol, respective alcohol, which can be done with lithium aluminum hydride, provided you work it out or work up with H2 in presence of H+. So this gives you the alcohol from the respective carboxylic acid. Let's go to the next one, which is the ester. So you have the ester, which is RCOOR. This is the ester. Once again, you work it out with lithium aluminum hydride in presence of H2O and H+, or even sodium in alcohol works out to supply nascent hydrogen, so that you get the CO group converted to RCOH, H and H. What about the OR? The OR here goes out as a second mole of alcohol. If I put this as R dash, so you will have R dash OH. So if the R is symmetrical, you get two similar alcohols, and if the R is unsymmetrical, like I've just replaced with R and R dash, you get two molecules of different alcohols. So this finishes the preparation of alcohol from the ester. Going on to yet another method from an aldehyde. So first method which we have spoken about is an aldehyde being treated with a reducing agent like hydrogen, lithium aluminum hydride, sodium borohydride. But now this aldehyde is being treated with a Grignard reagent. So let us go to our Grignard reagent. The Grignard reagent, the alkyl group is negative, as you know. So the negative gets attached to the carbon. Now why carbon? Because carbon is delta plus and oxygen is delta minus because of the difference in electronegativity between carbon and oxygen. So the R attaches to the carbon. You form the complex HCHOMgX and the R is here. You need to definitely write the complex when you're writing any board exam. Any written exam demands the complex to be written down. And after you do the hydrolysis, the OMG is just replaced, the MgX is just replaced with OH. So you get your alcohol here instead of the MgX. The MgX is replaced with H. And what about the MgX? It goes out as the side products, hydroxy magnesium halide. So that was with formaldehyde. Formaldehyde and Grignard gave you a primary alcohol. If you take not formaldehyde, any other aldehyde excepting formaldehyde, you will land up with a secondary alcohol. The mechanism is the same like before. If you have missed it, just rewind it and watch it once again and you're through. So you'll get a secondary alcohol and you take a ketone, react it with a Grignard, you'll get a tertiary alcohol, and the method of preparation of alcohol is done from an aldehyde and a ketone, once again giving you, the degrees are different, 1 degree, 2 degree, and 3 degree. Going on to the 9th method, which is from the ester, but now the ester is not being reduced. It is again being treated with a Grignard. All right, it is being treated with a Grignard. So once again, the RMgX comes into picture. R is minus. Once again, the same reaction. I'm not doing the mechanism. So once again, you get RC double bond OR. And if you get a ketone, you know that, your ORMgX. Once again, you get a ketone. We don't want to stop at the ketone. So just like we have reacted a second molecule, a second mole of Grignard, and you can get the respective alcohol. Yes, we have already done this before. Here, just done it here. Okay, from the ester, you think that you'll get a ketone. Again, take the second mole of Grignard, and you're successfully getting an alcohol. You get a 3 degree alcohol here. But in case you take the ester from formic acid, alkyl formate, then you do not get a 3 degree alcohol, you get a 2 degree alcohol. I hope it is clear. So I will do both the steps together. You have H, C, double bond, and the R coming from RMgX. And again, you take RMgX. So you will get HCO HR and the second R. So this is how you get the secondary alcohol. Now to the next one where you have an alkene and you want to get an alcohol. So you get an alkene, we have alkene double bond CH2. So when we take cold and concentrated sulfuric acid, water plays the main role. I am not doing the mechanism once again. We can look at the mechanism in the textbook. So the main shortcut is to add the OH on the carbon having less number of hydrogen following Markovnikov's rule. And again, the kid is hungry, so feed it because there's a double bond. The kid is hungry, feed it. So OH goes to the carbon. You have to remember the criteria. One, if it is unsymmetrical addendum, you have to follow Markovnikov's rule. So this is what is to be followed. And the H being positive adds to this carbon. And you get your OH attached to the second carbon to give you the product of the reaction. So this is how you get your alcohol. Okay. And if you want the anti-Markovnikov's addition of OH, what do? You have to add PH3, which is your borane, or B2H6, which is your diborane. Any way you do it, you will get the anti-Markovnikov addition of OH. And it is obvious that BH3 is a hydride, so the hydrogen will get attached to the carbon having less number of hydrogen following again Markovnikov's rule. So the hydrogen goes to the central carbon. And the OH, which is coming from the hydrogen peroxide supplied in alkaline condition, replaces the OH on the terminal carbon. So if you want Markovnikov's addition of OH from an alkene, you will have to use cold concentrated H2SO4. And if you want anti-Markovnikov's addition of OH on the terminal carbon with the carbon having more number of hydrogens, just use a hydroboration method. Okay, so this finishes the methods of preparation of alcohol. So let's go on to the chemical properties of alcohol. Let us start. Let us take the alcohol treated with sodium metal. When we treat it with sodium metal, what will you get? You will get the hydrogen displaced with sodium. Sodium being more reactive compared to hydrogen, it will replace the hydrogen with sodium and you'll get RONA, which is the sodium alkoxide, liberating hydrogen gas. Same with magnesium, because it's a divalent metal, you will get the magnesium alkoxide when you treat it with magnesium. Catch up with. Next, let's treat an alcohol with a carboxylic acid. If we treat an alcohol with a carboxylic acid, we will get an ester. You know that alcohol and the carboxylic acid, the OH and the H will leave as water, and what you are left with is RCO. Okay, you are left with RCO and the OR. The next reaction is alcohol, once again reaction with acyl halide. RCOCl is acyl halide. If you react with acyl halide in pyridine solvent, you will get RCO, OR, or R dash, whatever it is, you get an ester once again. If you take an anhydride, so the RC double bond O, C double bond OR, the anhydride, once again, the side product will be RCOOH, giving you the ester RCOOR. All right, RCOOR, once again, you get the ester. The next reaction is if you take a tertiary alcohol. If you take a tertiary alcohol, the 3-degree alcohol, and you react it with anhydrous zinc chloride in presence of HCl, the Cl will substitute the OH and you will get the alkyl halide, giving you the side product as water. So if you speak about the reactivity of the alcohol, it would be the 3-degree alcohol, which is more reactive because of the formation of the carbocation, 3-degree carbocation, which is very stable. 3 degree greater than 2 degree greater than 1 degree. Same thing you can do it with HBr. The OH will get replaced, the OH will get substituted with Br and you get the alkyl bromide along with the side product as water, similar to the reaction with HCl. But because HI and HBr are more reactive compared to HCl, you do not require any catalyst for this matter of fact. So HI, so once again, if you take HI, the H and the OH will form water and you will get the alkyl halide as the product of the reaction. The next reaction with PCl3, we had done it in the previous video also, which I had recorded. So here you will get RCl if you take PCl3 with the side product is H3PO3. If you take PCl5, the main product would remain the same and RCl, and the side product will now change to HCl and POCl3, phosphorus oxychloride. Next reaction with thionyl chloride also, we will get the main product, thionyl chloride in presence of pyridine as solvent. The main product will be RCl, giving you the side products as SO2 and HCl, which we have spoken of before also. Okay, so we have finished this reaction. Let us go to the next reaction with concentrated sulfuric acid. With concentrated sulfuric acid, if you want an alkene, we will speak about this. We have spoken about this reaction later also. So if you take the alcohol, and give concentrated sulfuric acid, which is a dehydrating agent, and you want an alkene, you would have to keep the temperature at 443 Kelvin. Then you get the product as alkene. Remember the temperature? It's very, very important. Next, if you want to convert an alcohol to an aldehyde or a ketone, you've got to use partial oxidizing agents, which is PCC or PDC, PCC, pyridinium chlorochromate, PDC, pyridinium dichromate. So the alcohol will get converted to the aldehyde or the ketone, depending whether the alcohol is primary or secondary. Okay, so you get an aldehyde or a ketone. If you take a strong oxidizing agent, which is potassium dichromate sulfuric acid, potassium dichromate sulfuric acid can partially oxidize it to an aldehyde or a ketone. But if you take a very strong oxidizing agent like potassium dichromate sulfuric acid and allow the oxidation to move ahead, you will get from the alcohol the respective carboxylic acid. So strong oxidation of an alcohol with a strong oxidizing agent gives you a carboxylic acid. Okay, here. So you have to prolong the reaction in order to get the carboxylic acid. And the last reaction is, once again you take the alcohol, you take 2 moles of alcohol now. Once again you add the same reagent as you had done before, concentrated sulfuric acid. So this time there is intermolecular dehydration. Between 2 molecules of alcohol, water is eliminated and you get the product as ether. I hope you have looked at the temperature. Now is 413 Kelvin. So if you want an ether, the temperature has to be 413 Kelvin, and that is how you get the respective ether. So with this comes to the end of alcohol. We are continuing with phenol in the next slide. So let's carry on. Let's start with the first method. So the first method you can use for prepare phenol is by Dow's process. What does Dow's process do is you take haloarine, react it with aqueous sodium hydroxide, maintain the temperature of 623 to 300 atmosphere pressure. See, it's very important to remember the pressure and the temperature of this particular reaction. Okay, then you get a nucleophilic substitution reaction where the chlorine is replaced with ONA. So you get sodium phenoxide, you acidify it, and then you get phenol. So this is how you can prepare phenol by Dow's process. Going on to the second method, you will start with benzene, add oleum there. Oleum is pyrosulfuric acid, which is S2S2O7, or you can call it fuming sulfuric acid, or you can take concentrated sulfuric acid where you get benzene sulfonic acid. Then you treat it with sodium hydroxide. You can write one more step here where you get sodium phenoxide. Why? Because you have SO3H, which is a good leaving group. And then you acidify it. Once you acidify it, you get phenol. All right, so this is how it goes. If you want, you can split it up to one more step, sodium phenoxide and then to phenol. So here goes the method of preparation of phenol from benzene. We can also prepare phenol from a diazonium salt. So a diazonium salt is taken where you have a diazonium salt, and if you want to once again revise like how the diazonium salt is prepared, it is prepared from aniline, and you use NaNO2 HCl, maintain a temperature of 0 to 5 degrees Celsius. You get the benzene diazonium chloride, and then you simply treat it with warm water. N2 being a good leaving group will leave as nitrogen gas, and you get phenol and HCl as the side products of the reaction. Next, going on to the next method of preparation of phenol, it is from cumene. Cumene is isopropyl benzene. Cumene is isopropyl benzene. What do? In isopropyl, in cumene, you put oxygen or air, and that will help you to get cumene hydroperoxide. This is cumene hydroperoxide. So this cumene hydroperoxide, when acidified with dilute any acid you can take, you get phenol and acetone. So there's a rearrangement taking place here where you can learn the shortcut, the benzene and the OH connecting to give you phenol. And in between, you're left with 3 carbons, which will help you to form acetone. Okay, so with this finishes the methods of preparation of phenol. Going on to its reactivity, the first reaction we can take up is phenol reacting with carboxylic acid to give you ester. You can take, for that matter of fact, any carboxylic acid. You get this ester. In case you've taken phenol and butanoic acid, which is the example that's stated here, phenol and butanoic acid. So the OH and the H will give you an ester. What about the name of the ester? You name the group attached to oxygen first. So this is phenyl. And this is a butanoid. So this is phenyl butanoate. In case you want to, we have spoken about this before also, that if you want to halogenate phenol, you will take HX, any halogen acid with phenol. Under special conditions, you will get the haloarene. This is another example where you take phenol and PX3 or any PCl3, PI3, you will get the haloarene along with phosphoric acid as a side product of the reaction. Going on to the next one, which is electrophilic substitution of phenol. What do we mean by electrophilic substitution reaction? The phenolic group being an orthopara directed due to resonance, right? You know that the OH group of phenol is an orthopara director. So the ortho position is negatively charged and the para position is also negatively charged. So when we do a nitration reaction, the NO2 plus, which is the nitronium ion, gets attached at the ortho and the para position, giving you a mixture of 2 products, ortho and para. Now, in case of dilute nitric acid, you get a mixture because the reaction is slow. And when the reaction is slow, you get a mixture of products, giving you the side product as what? If you want, you can balance the reaction. I mean, if you want, you can balance the reaction or leave it unbalanced, because in organic chemistry, balancing does not, the marking scheme does not take into account the balancing of organic reactions. So here, in case you are wanting to balance it, no problem, you go ahead. And then you get the side product as water. The analysis of nitration is, we have done it before also, HONO. So this is plus, this is minus. So you understand the side product. Now, in the other reaction you can see, which is displayed, again, we are doing a nitration reaction, but this time we have changed the reaction condition to concentrated nitric acid. So in case of concentrated nitric acid, what happens is that the reaction is fast. The reaction is happening fast. So that makes a simultaneous attack at the ortho and the para position. The nitronium ion, being the electrophile, attacks all the electron-rich positions simultaneously, giving a trinitrated product, which is picric acid. Note it down. If you feel that you have to pause, take a break, note it down. Pause. Yes. Going on to the next one, which is halogenation reaction. In halogenation, here this halogenation is different from the halogenation that we have discussed before. Here the OH group is there remaining. We are doing an electrophilic substitution reaction. We are not knocking out the OH group. So in case you're doing a bromination reaction and you want a slow reaction to happen or a fast reaction to happen, you've got to actually change the reaction conditions. So in this case, if you have taken 273 Kelvin, which is 0 degrees Celsius, all right, compared to bromine water, which is done at room temperature, when something is not, and when any temperature is not mentioned, you have to understand that the reaction is being carried out at room temperature. So obviously the room temperature is higher compared to the 0 degrees Celsius temperature. So you can make out that the second reaction will be faster compared to the fast reaction. So first reaction, so in this case, bromination with, so this is slow and this is fast. So the reaction is slow, it will give you a mixture of products. So here, since bromination is happening, bromine along with the non-polar, non-protic solvent. All right, there's a solvent effect in the product, in the formation of product also. So in this case, bromination happens slowly at the ortho and the para positions, giving you orthobromophenol and parabromophenol. In case of the fast reaction, which is happening with bromine water at room temperature, you get a tribrominated product, which is 2,4,6-tribromophenol. So if you are inquisitive to know whether Friedel-Crafts alkylation and acylation is possible with phenol, yes, it is possible, but under very harsh and drastic conditions, which I will not discuss right now. So another electrophilic substitution reaction we can do is a sulfonation reaction. So if you have phenol and you react it with oleum concentrated sulfuric acid, a fuming sulfuric acid, you will get phenol, and depending on the temperature, you will get the ortho or the para product. A higher temperature gives you a para product, whereas a lower temperature gives you the ortho product. In case you're interested, you can write this reaction down about the temperature guided product of the reaction. Going on to the next, the named reaction, coal-base reaction. In coal-base reaction, the phenol is first. What is the ultimate outcome of coal-base reaction is salicylic acid. So if you take phenol and treat it with sodium hydroxide, you are activating the ortho position, to such an extent that you can make an electrophile come and get attached at the ortho position. So in this case, carbon dioxide being the electrophile, it comes in, gets attached to the ortho position of phenol, and after acidification, if you want, you can write an intermediate where both are in the salt state, the sodium salt state, and then once you acidify, you will get the salt Na removed and the acidified product, which is salicylic acid. This is salicylic acid. Okay, moving on to the next reaction, which is the Remer-Tiemann reaction. In Remer-Tiemann reaction, we have phenol. What is the ultimate outcome of Remer-Tiemann reaction is salicylaldehyde. And why these are important? Because be it salicylic acid, that is directly used for the preparation of aspirin. Okay, and Remer-Tiemann reaction also we get salicylaldehyde. We get salicylaldehyde. This salicylaldehyde can also be oxidized to give salicylic acid, which is again used as a precursor for preparing aspirin. Okay, so in Remer-Tiemann reaction, what is done is that phenol is treated with chloroform in presence of sodium hydroxide, so it gives you an intermediate. Right, it gives you an intermediate. And then we are not doing the mechanism of the reaction where it involves a dichlorocarbene intermediate. We'll surge ahead because it's a quick revision. So after you get the intermediate, then you treat it with NaOH aqueous, where both the Cls are substituted with OH. The OH on the geminal OH, they undergo repulsion, and because of the repulsion, it loses water and gives you an aldehyde group. After the final acidification, you get salicylaldehyde. So this is about Remer-Tiemann reaction. So the substitution reactions, the electrophilic substitution reactions are done. And now we go on to special reactions like treatment of phenol with zinc dust. If you treat phenol with zinc dust, zinc has a very strong affinity for oxygen. So what will it do? Steal the oxygen away and give you benzene along with zinc oxide as the side product of the reaction. And the last but not the least reaction is phenol with undergoing a vigorous oxidation with sodium dichromate and sulfuric acid. So what you get is benzoquinone. This is benzoquinone. Remember, you have to be very careful about writing the bonds. Do not write it this way. Do not write it this way. This is wrong. Okay, so see where exactly the bond positions are. Okay, so this is benzoquinone, which is the product of the reaction. Let's continue with the methods of preparation of ethers. So to prepare ethers, you can start from 2 molecules of alcohol. So you have, say, methanol, and you take the second molecule of methanol once again. You put a dehydrating agent, concentrated sulfuric acid. So what will happen is that at 413 Kelvin, remember the temperature, it's very, very important to remember the temperature. 413 Kelvin, there is dehydration reaction, H and OH going out, and you'll get the CH3O connected with the CH3, giving you the ether, along with the side product as water. So in this case, I've taken ethanol. It will give you diethyl ether as the main product of the reaction. So this is how ethers are prepared, starting from alcohols. Going on to Williamson's synthesis. In Williamson's synthesis, you take an alkoxide. You take an alkoxide. Alkoxide means sodium salt of alcohol. Sodium salt of alcohol is called an alkoxide. You take a sodium alkoxide. In this case, I've taken 1, 2, 3, 4, 5. A sodium pentoxide. All right. Sodium salt of pentanol. That is sodium pentoxide. So that is treated with an alkyl halide. If you ask me any alkyl halide, the answer is yes. So I have taken propyl chloride, and then I have got this ether where a metal will always pick up a non-metal. A metal has a very high affinity for the non-metal, it is so understood. And the oxygen, all right, take up the counterpart of the alkyl halide. So it gives you propyl pentyl ether. Of course, I've said the common name, propyl pentyl ether. So this is how Williamson used his method to prepare alkoxides. If you are looking for a branched ether, if you're looking up to prepare a branched ether, then you have to take a branched alkoxide. If you take a branched alkoxide, then you are able to do the ether preparation, or else not. Okay, so your question is obviously, what will happen if I don't take a branched alkoxide? Okay, chalo. Like in this case, we have taken a sodium tertiary butoxide, and I have taken once again propyl halide. So I've got the tertiary butyl propyl ether. So your obvious question is that if you do the reverse, then what will happen? So that is why we have taken up this reaction. If you do the reverse, you take a branched halide. You will not get an ether in this case. You will not get an ether. So it will undergo an elimination reaction and you will get an alkene. How does it work? So the sodium propoxide in this case, it starts behaving as a base. So it starts behaving as a base, it will start looking out for a proton. So this proton is being picked up by the base, and then an elimination reaction happens. All right, a beta elimination reaction happens and you land up with an alkene. Right, you land up with an alkene. Okay, let's apply this to get an aromatic ether. So we take sodium phenoxide. Yes, this is sodium phenoxide. You take any, say, methyl halide, methyl chloride, etc. So once again, the same logic works here. NaX goes out a side product of the reaction. And you get, yes, you're right, it is anisole. You get anisole. So this finishes the method of preparation of ethers. Going on to the chemical reactions of ethers. If we take diethyl ether and react it with any halogen acid, any halogen acid. Then what will happen is that I've taken a symmetrical compound for this matter of fact. You will, split the OC bond. You will split one of the OC bond, and the oxygen will take up the hydrogen of the alkyl, the halogen acid, and will give you an alcohol, and the other counterpart will give the halide. Right? So the diethyl ether, when reacted with hydrogen halide, will break one of the OC bond. And whichever side you have the oxygen, that has a strong affinity for the hydrogen of the halogen acid. So you will obviously get an alcohol, and the other part will pick up the X. So you get the alkyl halide. So with a hydrogen acid, you will get the respective alcohol and the alkyl halide as the main product of the reaction. So now here a question may come, like you have a highly branched alkyl halide and a small, halide, alkyl chain on one side. So you take a hydrogen halide, the small chain has a probability to take up X, and the long chain has a probability of taking up the OH. Okay, the long chain picks up the OH. The mechanism is definitely there for the reaction. So in this case, say I take an easier example. Say you have CH3O along with HI. I'm given an example of this type. Once again, another example. So the smaller group will pick up the I, and you will get CH3I along with OH. Okay, so here the logic is that there is a lot of double bond character. So naturally, it is difficult to break the benzene oxygen, the benzene carbon and the oxygen bond. So that bond remains intact. So you get phenol along with the alkyl halide. Here there's a second example with a difference. You have a branched ether now and a non-branched ether. You have a tertiary butyl ethyl ether. So if you have a tertiary butyl ethyl ether, then as you already know, that you would look out for breaking the OC bond. Which OC bond would you prefer here to be broken? I would prefer the tertiary carbocation to get formed because of more stability compared to the ethyl carbocation. So if you have guessed it correct, yes, this is the carbocation which is formed, the tertiary butyl carbocation, and that gives you the tertiary halide as the product. This is the cation, so it will definitely have an affinity for the halide and the ethyl alcohol, which is the main product of the reaction. Okay, so you have to remember to judge the products according to the stability of the carbocation, seeing the SN1 mechanism or an SN2 mechanism to judge the correct products of the reaction. Going on to the electrophilic substitution reactions of anisole. So if we have a bromination reaction happening, once again, because of the OCH3, the methoxy group being an activating group, it activates the ortho and the para position once again. So a bromination in ethanoic acid gives you a mixture of orthobromoanisole and parabromoanisole with the side product as HBI. Once again, you know that ethers are unreactive, very slow in their reactivity. So what happens is you get the slow product always gives rise to a mixture of products, which is the ortho and the para. So remember, whenever you're doing all the reactions of ethers, you will get a mixture, mostly a mixture. So if you do next the Friedel-Crafts alkylation reaction. If you do the Friedel-Crafts alkylation reaction, the alkyl group, the propyl group would come in at once again the ortho and the para position. Okay, you get the alkylated product of anisole at the ortho and the para position. If you are doing an acetylation reaction with, say, acetyl chloride, ethanoyl chloride, along with anhydrous aluminum chloride, here the condition was anhydrous aluminum chloride with carbon disulfide. Here also you take anhydrous aluminum chloride, you require the Lewis acids. So here the acetylation or acylation occurred at the para and the ortho position, giving you the side product as HCl. And a nitration reaction would give a nitro at the ortho and the para position. Okay, so once again, you get orthonitroanisole and paranitroanisole along with water as the side product of the reaction. So this concludes the chapter of alcohol, phenol, and ether. Once again, I would take up MCQs and assertion reason to wind up this chapter once and for all. Let's wind up with the MCQs. Which of the following phenolic compounds is most acidic in nature? You know that electron withdrawing groups, if attached to phenol, it's most acidic. Electron withdrawing groups make the hydrogen highly acidic. So we have, now the question is, we have amino which is donating without any donating groups, only phenol, metanitrophenol and paranitrophenol. So I've taken up this question just to make you understand that, there is an electron withdrawing group present in both. But, the paranitrophenol is more acidic because paranitrophenol is more acidic because the electron withdrawing group is at the para position, and phenol being an activating group, it gets the nitro group attached at the para position gets more activated, making the hydrogen of phenol more acidic. Next, the seventh one, isopropyl methyl ether when treated with cold HI. Let's write the reaction. This is isopropyl methyl ether. See, we have a branch here. So the isopropyl methyl ether when treated with cold HI, now you've got to be judgmental regarding which of the CO bonds will get cleaved. So is this OC bond getting cleaved or is this OC bond getting cleaved? So according to the concept that I've already taught you, that CH3 will take up the I to give you methyl iodide, because here the stable carbocation will be generated with the plus I effect operating. So here the answer is isopropyl alcohol and methyl iodide. If you have thought that as the correct answer, it is very good. Going on to the next one. Ethanol when treated with PCl5, ethanol will treated with PCl5, you will have the OH of ethanol replaced with Cl, so you'll have C2H5Cl. C2H5Cl when treated with alcoholic KOH will give you the alkene. And the alkene when treated with H2SO4 at room temperature, it gives you back ethyl alcohol. So once again, you started with ethanol and you got the answer as ethanol, which is the correct answer. So the option is D. Which of the following compound is most acidic, just like the previous question, but with a small difference here? And the difference is you have an alcohol also given, you have phenol given, and if you have guessed the correct, it is the electron withdrawing group, which makes the compound most acidic. So C is the correct answer. The reaction involving dichlorocarbene as electrophile. While speaking, I had mentioned about the dichlorocarbene intermediate coming into picture in Riemer-Tiemann reaction. If you have heard it correct, you will get the correct answer, and that is A. And let's discuss the assertion reasons. A, B, C, D, E options are displayed on the screen. The boiling points of alcohols are higher than that of the hydrocarbons of comparable molecular mass. So the boiling points of alcohol are definitely higher compared to the hydrocarbons of comparable molecular mass, because alcohols, they undergo hydrogen bonding compared to hydrocarbons which have van der Waals forces. Yes, and alcohols show intramolecular hydrogen bonding. So alcohols do not show intramolecular hydrogen bonding. Phenols can show. So the option is C. The assertion is correct, but the reason is incorrect. So here the answer is C. Okay. So going on to the next one, I hope you all are convinced that the answer is C. Going on to the next one. Phenol undergoes Kolbe's reaction, but ethanol does not. It is correct. Phenol is more acidic than ethanol. That is also correct. But do you think the reason is being supported by the assertion? No. They are independently correct, but the reason does not support the assertion. So the answer for this is, if you have said B, the answer is correct. Next one, the COC bond angle in ethers is higher than that of water bond angle, HOH bond angle in water. The HOH bond angle in water, because oxygen contains two lone pairs, the bond angle in water is 104.5 degree. All right, compared to the bond angle in ethers, which is 109 degree approximately. So oxygen in both ethers and water is sp3 hybridized. That is also correct. And the COC bond angle in ethers is higher than the HOH bond angle in water. That is also correct. But the reason does not once again support, it's not because of the hybridization, it's because of the lone pair bond pair repulsion that the squeezing in the bond angle in water happens. So independently they are correct, but the reason does not support the assertion. So B is once again the correct answer. Now for the fourth one, the boiling point of diethyl ether is much less than ethanol. Correct. Diethyl ether are, they're hardly polar. Their polarity is minimized compared to ethanol, where it is highly polar because of the electronegative difference between the oxygen and the hydrogen. Correct. In ethanol molecules, they are associated by intermolecular hydrogen bonding, whereas in diethyl ether, that intermolecular hydrogen bonding is not possible. And that is the reason for the low boiling point or the volatile nature of alcohol, because of the absence of the intermolecular hydrogen bonding. It's correct. So the answer is A, correct, the fourth one. And alcohols have higher boiling point than ethers of comparable molecular masses. Alcohols, definitely the above question and the next one is definitely interconnected. And alcohols and ethers are isomeric compounds. You know that alcohols and ethers are functional isomers of each other. But that's not the reason for the assertion. Fine? It's because of intermolecular hydrogen bonding. So I think this was a very easy guess. B is the correct answer. So the assertion reasons, I hope it went right in. Do look forward. Thank you for watching.